students. Before the holidays, we have left our topic on preparation of haloarenes. So I'm starting from the same point. Preparation of haloarenes can be done by direct halogenation. And in that direct halogenation, we can prepare chlorobenzene as well as a bromobenzene. But if you see in these two reactions, chlorine and bromine is made to react with benzene ring at a low temperature of 310 to 320 Kelvin in the presence of anhydrous FeCl3 or anhydrous AlCl3. Here your anhydrous FeCl3 or anhydrous AlCl3 is working like a Lewis acid and is helping in the direct substitution of chlorine or bromine on the benzene ring. My dear students, if you will be using sunlight, that will not help in the direct substitution of halogen on the benzene ring. Rather than it will help in the side chain halogenation, which we will talk later on. But first, if you see this reaction, anhydrous FeCl3 or anhydrous AlCl3, it is playing very important role as a Lewis acid and is helping in the direct substitution of halogen on the benzene ring. So in this way we can prepare chlorobenzene as well as bromobenzene. If I talk about preparation of iodobenzene, as I am showing you in the next reaction, iodobenzene, it is, if you see the sign which here it is shown, that is reversible. That means iodination reaction is reversible. Why it is reversible? Because of the formation of HI. If you want to carry this reaction in the forward direction, then you need to oxidize this HI. And how you'll be oxidizing this HI? For that you need to add oxidizing agents. Here we can use any of the three oxidizing agents like HiO3, hydroiodic acid, HNO3 nitric acid, or HGO, mercuric oxide. Any of the three you can use, as I am showing you here, HiO3, HNO3 or HGO. How it will help you in oxidizing HI? I'll show you with the help of the reactions. If you see in the first reaction, HI is getting oxidized with the help of nitric acid to iodine. And if you're using hydroiodic acid, it will be oxidizing HI to iodine. If you take mercuric oxide, then it will be oxidizing HI to mercuric iodide. So in this way, your HI, that is HI, will be oxidized to either iodine or mercuric iodide. And likewise, your reaction will be forwarded in the forward direction. So this way you can prepare your iodobenzene. If we move forward towards your next two important reactions, if you see, I have taken toluene in these two reactions and I'm making it react with chlorine in the presence of FeCl3, and in the second reaction I'm making it react with sunlight. If you see first reaction, if you're using Lewis acid helps in the direct substitution of halogen on the benzene ring. And if you see, the chlorine is getting substituted at ortho and para position with respect to the methyl group attached to it. And if you see, if you're using sunlight, then instead of the direct substitution on the benzene ring, the side chain halogenation is taking place. This is a very, very important concept. If you're using sunlight, then side chain halogenation will be taking place. And where is your side chain? That is on the methyl. CH3 is working like a side chain. CH3, it is getting substituted with Cl, and your hydrogen is getting removed in the form of HCl. So here your side chain halogenation is taking place in the presence of sunlight. Whereas if you are using anhydrous FeCl3, then direct substitution on the benzene ring at ortho and para position is taking place. Corresponding to the same category of reaction, I'll take one more example. Here, if you see, I have taken ethyl benzene. Earlier I have taken toluene, which is also known as methyl benzene. Here I have taken ethyl benzene. Now, when your side chain which is connected to the benzene ring is larger, then how that halogenation will be taking place and in the presence of sunlight. Then out of now, here two carbons are there, CH2, CH3. The halogenation in your mind, it can take place from CH3 also and CH2 also, but keep this thing in mind that when side chain halogenation takes place in compounds like these, when side chain is connected to the benzene ring, the substitution will be always taking place at the benzylic position. That means benzylic carbon, which is the CH2 carbon, this is the benzylic carbon. The substitution will be taking place at this benzylic carbon. And if you see again, it is getting substituted Cl at benzylic position. So however long chain you have with the benzene ring, the side chain substitution or side chain halogenation will be only taking place at the benzylic carbon. This is also known as benzylic halogenation. We can also call it as a benzylic halogenation. This is a very important category of reaction. Corresponding to the side chain halogenation, one more example I'm having with you is toluene when made to react with sulfuric chloride. Here I have taken sulfuric chloride with traces of peroxide at a temperature of 475 Kelvin. And again, sunlight, in the presence of sunlight, this reaction is carried out. Here we are getting benzyl chloride as the product. If you see, benzyl chloride is this, and your SO2 and HCl that is escaping from the reaction mixture, and pure benzyl chloride is obtained. So this is again one of the very good category of reaction for the preparation of benzylic chloride by the side chain halogenation. If you remember, in the previous concept before the holidays, we have done about N-bromosuccinamide, NBS, and it is used for the allylic substitutions. So here again, if you use this here in this reaction, again allylic substitution, it is a kind of allylic substitution. This is a allylic carbon, CH3. So allylic substitution, it is taking place in the same way, side chain substitution. So yeah, NBS again, it is helping in the side chain halogenation. Here I have done side chain bromination. So NBS and bromosuccinamide. If you want to prepare benzyl bromide, then you can use NBS also, as we have done in allylic bromination also earlier. So N-bromosuccinamide with traces of peroxide can be used for the preparation of benzyl bromide. Now I'll continue with the same, but before preparation of haloarenes. But for that, I'll discuss some important naming reactions with you. And in that important category of naming reaction, we are having Sandmeyer's reaction. Sandmeyer's reaction is a very important reaction which is used generally for the preparation of chlorobenzene, bromobenzene, and iodobenzene. But if you see in all these reactions, Sandmeyer's reaction, we are using this compound which is called BDC, benzene diazonium chloride. So the basic thing which is required in the Sandmeyer reaction is BDC. So BDC is called benzene diazonium chloride. So you need to learn the preparation of BDC, how it is done. BDC can be prepared by treating aniline. Aniline is this one. Aniline with nitrous acid, and or you can directly take sodium nitrite and dilute HCl. If you see sodium nitrite and dilute HCl, you get nitrous acid, HONO. So either you can write these two, or you can write nitrous acid with little HCl. And the temperature is 0 to 5 degrees Celsius or 273 to 278 Kelvin. Here your BDC is prepared. This is your benzene diazonium chloride. It is very, very reactive in nature, and In your Sandmeier's reaction, we are using this BDC, benzene diazonium chloride. We are reacting it with cuprous chloride, CuCl, in the presence of HCl. Or if you want to prepare bromobenzene, you can take cuprous bromide in the presence of HBr. And what you will get the desired product, that is chlorobenzene. Nitrogen will be eliminated. Here bromobenzene, nitrogen and chloride and ion will be eliminated. If you want to prepare iodobenzene, then you can directly react this BTC with Ki, aqueous solution of Ki, and simply not heating is required, only warm. Then you can easily prepare your iodobenzene. And this is a very famous category of reaction. This comes under Sandmeier's reaction. Sandmeier's reaction. I'm continuing with the same. We have done the preparation of chlorobenzene, bromobenzene, and iodobenzene. Now for preparing fluorobenzene, you need not to prepare BDC by benzene diazonium chloride नहीं चाहिए यहाँ पे. In this reaction you need benzene diazonium tetrafluoroborate. Very easy method to prepare. If you react aniline with sodium nitrite, a small change you did, instead of taking HCl, you have taken fluoroboric acid, HbF4, and the temperature is same, 273 to 278. Here you get, instead of N2 plus Cl minus, here you get N2BF4 negative. Benzene diazonium tetrafluoroborate. If you heat this respective compound, you get fluorobenzene, and your nitrogen and boron trifluoride will be eliminated. So this is how you will be going to prepare your fluorobenzene, by using the same method. Only the change is that instead of HCl, you are using HbF4, fluoroboric tetrafluoroboric acid, and you are preparing benzene diazonium tetrafluoroborate. Corresponding to the preparation of chlorobenzene and bromobenzene, one more naming reaction we are having, which is known as Gator Man reaction. Gator Man reaction is quite similar to the Sandmeier reaction. I'm again showing you the same clip of Sandmeier reaction. If you see, in Sandmeier reaction we did BDC reacted with CuCl, that is cuprous chloride, in the presence of HCl, cuprous bromide in the presence of HBr. A small same process is there. Here you are taking BDC, but here you are taking copper, not cuprous chloride, not salt of copper. You are taking simply copper turnings in the presence of HCl, copper turnings in the presence of HBr. You are heating with them and you are getting the respective chlorobenzene and bromobenzene. Nitrogen will be eliminated. So this is again a very important category of reaction. Similar to your Sandmeier's reaction, only the changes in place of cuprous chloride, cuprous bromide, you are taking copper turnings. And this is a Gator Man reaction. Now with this, your preparation of haloarenes is done. Now I'm switching to the physical properties of haloalkanes and haloarenes. If I talk about the physical property, the very first thing which comes is their color. Pure alkyl halides, they are colorless, but they generally develop color, like your bromobenzene and iodobenzene. Generally they develop color when they are exposed to the sunlight. If I talk about the state, the lower members of their family, like your methyl chloride, methyl bromide, methyl iodide, they are gases at room temperature. If I talk about the higher members, if you go towards the butyl chloride, butyl bromide, butyl iodide, if you go further to the higher members, they are either liquids or solids. Now, very important concept regarding the boiling point. Boiling point, as I have already discussed with you, that Rx, R is alkyl group and X is your halogen, alkyl halide. This is a polar compound. I have already discussed about the polarity of the compounds. Because of the electronegativity difference between the halogen and the carbon, this bond becomes gets polarized, and because of that polarization your halogen acquires slight negative charge and your carbon acquires slight positive charge. The bond gets polarized. So due to the polarity, they have higher boiling point if you compare them with the hydrocarbons of the same molecular mass. Here I'll show you with the example. If you see in this example, methane, which is a hydrocarbon, having boiling point 111, and if you see, as the mass increases, methyl fluoride 195, CH3Cl 249 Kelvin, as the size of the halogen increases, what is happening? Size of the halogen increases, the boiling point is increasing. The boiling point is increasing. If you see, the highest boiling point is in the case of methyl iodide. And what is the reason for this? The size of the halogen is increasing, the surface area is getting increased, and the van der Waals force of attraction is also getting increased, and because of that increase, the boiling point is automatically getting increased. And if you compare with this, in this case the bond is not polar. The bond is not polar and the boiling point is very low. So that is why I'm saying that due to the polarity of higher molecular mass, boiling point of alkyl chloride, bromide and iodide is always higher than the corresponding hydrocarbons. If you are having same halogen and the chain is like this, if you see, halogen is same, but the chain is, here it is methyl chloride, ethyl chloride, propyl chloride, butyl chloride. The boiling point of butyl chloride is maximum, then is your propyl chloride, then is your ethyl, and then is your methyl. Now again the same reason. Why? Because if you see, the chain length is increasing, surface area is increasing, the van der Waals force of attraction will increase, and so will be the boiling point. So that is why, that is the reason that boiling point of your butyl chloride is more than that of your propyl, and in comparison to your ethyl and methyl chloride. Starting with the same, if I take the example of this isomeric alkyl halides. Isomeric alkyl halides, if I'm talking about, this is your butyl chloride, 4 carbons. If you see carbons, 4 carbons are there, hydrogens 3, 4, 5, 6, 7, 8, 9. 9 hydrogens, 1 chlorine. If you see here also 9, 3, 3, 6, 7, 8, 9. 3, 3, 3, 9 hydrogens, 4 carbons and chlorine. These all are isomers, same molecular formula but different structures. If you see the boiling point variation, the boiling point is decreasing with increase in branching. Again, I'll take you back to your 11th class. This concept we have done in hydrocarbon also. In case of isomeric alkyl halides, the boiling point decreases with the increase in branching. Why? Because if you see here in the straight chain, the surface area is more, and as the branching is taking place, the surface area is decreasing. Here almost the molecule is becoming spherical, so the area of contact will be less between the molecules, and the van der Waals force of attraction will be also decreasing with increase in branching, and so will be your boiling point. So with the increase in branching, what is happening? The boiling point is getting decreased. Now, if the number of halogen atoms increases, if you see, the boiling point is increasing with the increase in number of halogen atoms. That is automatically understood. If number of halogen atoms it is increasing, the molecular mass will be increasing, and so will be the boiling point. Now I'll talk about the haloarenes. The melting point and boiling point of haloarenes increasing with increase in the size of the halogen. If you see, iodobenzene 462 Kelvin boiling point, and if you see fluorobenzene 358. So that means this iodine is making the difference, and here fluorine is making the difference. The size of iodine is larger than that of your fluorine. For isomeric dihalobenzene compounds, if you see isomeric dihalobenzene compounds, if you see their boiling points, I'm talking about orthodichlorobenzene, metadichlorobenzene, paradichlorobenzene. If you see their boiling point, there is no much difference between their boiling points. But if you see the melting point of this ortho dichlorobenzene is less and your para dichlorobenzene is high in comparison to both of them. The reason is this para dichlorobenzene being a symmetrical. How you'll be judging that it is symmetrical? If you divide this, you will get two symmetrical structures, and this is a symmetrical compound, so it fits in the crystal lattice. And that is why, being symmetrical in nature, fits in the crystal lattice. That is why it is having high melting point in comparison to ortho and para, which are not symmetrical. So this question has come in recent board exam also. So why the boiling point of this your para isomer is more in comparison to ortho and meta? Because of its symmetrical structure, it fits in the crystal lattice. That is why the boiling point of this para isomer is more in comparison to melting point of this para isomer is more in comparison to ortho and meta isomers.